In the field of science and huge mysteries, the subject of what existed prior to the enormous explosion has blended conversations and intrigued thinkers for quite a while. This huge question doesn't just test how we could decode the universe, it poses a challenge to the genuine furthest limits of human knowledge. Imagine standing at the edge of existence, looking into the colossal shadow and pondering what lay there, what existed before our universe was imagined. The event of the Big Bang marked the beginning of time, space, and all that we know. Anyway, was there a second earlier than this? Could there have been a condition of nothingness, a calm before the cosmic gathering began? And if this is true, was it, or perhaps, was there something much more alarming that existed previously, before time itself? As we continue with this inquiry, science takes us on a journey beyond the insight into the beginning of the universe, one that challenges our consciousness. Physicist Brian Cox, well known for his investigation into the wonder of the universe, suggests that something surprising might have existed before the massive explosion. He directs us to reconsider our understanding of reality and existence. In this examination, we'll dissect the science, the speculation, and the dazzling secrets that might explain what happened before everything else. We'll explore thoughts like self-importance, quantum changes, dark energy, and even multiverse. The answers we reveal might just paralyze you, yet they could also open up new perspectives on our position in the universe. Get ready to dive deep into a world beyond imagination and science. In the midst of the obscure, scientists have been left in the shadows, flawed and sometimes even upset. We ought to explore what existed before the Big Bang, and why these theories test everything we thought we knew. To appreciate what may have existed before the Big Bang, we first need to painstakingly analyze what the Big Bang truly was. The Big Bang, as scientists define it, refers to the moment when the universe became extremely dense and hot, rapidly expanding to cause the growth of all matter and energy. When we look at the night sky, there are no boundaries. It reveals evidence of this hot beginning, with galaxies spreading out in all directions from the starting point. However, why did this happen? Furthermore, was there a time before this dense, hot start? According to the theory of cosmic inflation, there was indeed a time before. And it lacked any semblance of void or peace. Vast expansion suggests that the universe existed before the Big Bang, a state that was cold, vacant, and loose. It resembled a huge vacuum. However, this vacuum wasn't entirely empty. It contained a gigantic amount of energy that fueled the quick expansion of space itself. This expansion, called inflation, happened so rapidly that it essentially laid the groundwork for all that would follow, parts of space extending at unfathomable rates, until the expansion slowed down and the energy changed into particles of matter and the forces we observe as the Big Bang. But what was the nature of this energy? What purpose did it serve? Why did the universe suddenly expand? Why did it stop? Specialists believe that this immense expansion resulted in patches of the universe, each experiencing its own Big Bang. Imagine a fabric extending endlessly, with tiny pockets of air forming here and there, each air pocket representing a universe, including our own. This idea, called the inflationary multiverse, suggests that there are possibly limitless Big Bangs and an infinite number of universes. Our own is just one of many. This huge, mind-bending reality challenges our understanding of the universe itself and leaves us with the inquiry, what else is there? The idea of nothingness before the Big Bang is speculative, not real, at least according to our current understanding. Even if you remove all radiation and energy particles from the universe, it would still not be truly void. Our universe is filled with dark matter, dark energy, quantum fields, and other forces that weave an inevitable tapestry, even in its most vacant form. Even if we imagine stripping away all these forces, leaving dead space, the universe would still generate new kinds of energy. This reality alone is bewildering to specialists, as it suggests that true nothingness might be impossible within our comprehension. Space itself has constants, rules, and properties that prevent it from being totally empty. Imagine constructing a region with nothing in it, no particles, no radiation, and no energy, except quantum fields and major constants. These would still exist, suggesting that this nothingness has properties. For instance, there's a peculiarity known as zero-point energy, which represents the lowest possible energy condition of quantum fields. In this state, particles can still momentarily appear and vanish, making a spooky resonance of movement, even in what should be empty space. This challenges our concept of a genuine void. Indeed, prior to the Big Bang, there may have been something that scientists are only beginning to understand. One of the most astounding theories in current cosmology is the chance of timeless expansion. If inflation could destroy our universe, it's possible it could continue forever. Brian Cox gives an astonishing description of the inflationary multiverse, in which universes are infinitely created and continue expanding. Imagine each Big Bang as a flash lighting another universe. Inflation continues into areas that create numerous other universes. This cycle could, in theory, go on for eternity. This idea of vast universes creates an enchanting concept of a fractal universe, where each new universe may actually develop its own Big Bang. Every universe exists as a separate, independent domain, unaffected by the others, because of the rapid expansion of space. For researchers, this hypothesis is both exciting and unsettling. It suggests a never-ending multiverse with no predetermined beginning or end, our universe being just one bit in a giant cosmic structure, forever expanding and constantly making new universes. And what if the most upsetting fact is that there is no before or after? Rather, an eternal pattern of universes forming and decaying. Our understanding of nothingness changes when we consider quantum field theory. According to this theory, the universe is not merely a variety of subjects floating in space, rather, it's a complex energy field network that fills the universe, connecting to create all that we observe. These fields are like invisible seas, with particles acting as waves or disturbances. Even when fields are at their lowest energy level, known as the vacuum state, they are still alive. Particles can appear and disappear, momentarily acquiring energy before returning it. This phenomenon generates virtual particles, substances that immediately exist and then vanish, leaving only a hazy trace of their presence. The idea of virtual particles challenges the concept of a real void. Imagine an empty universe where all radiation and energy are eliminated. Would you have total nothingness? According to quantum field theory, you wouldn't. Even in a vacuum, fields remain active, sometimes creating transient particles. This movement in what should be nothing suggests that the universe doesn't recognize our concept of emptiness. The fields and forces continue to fill the universe with hidden energy that prevents total inertia. This understanding raises an intriguing question. Could carry evidence from the earliest moments before the Big Bang itself. These primordial gravitational waves might have been imprinted during the rapid inflationary period, or perhaps even before it, offering a glimpse into the state of the universe, or multiverse, that preceded our own. If scientists can detect and decode these ancient waves, it might validate the existence of a pre-Big Bang state. They would serve as echoes from a time beyond time, carrying information about the physics that governed existence before matter, light, or even time itself came into being. Another area of exploration lies in string theory and loop quantum gravity. These advanced frameworks aim to unify general relativity and quantum mechanics, potentially offering a window into the pre-Big Bang cosmos. String theory suggests that the fundamental constituents of the universe aren't particles but tiny, vibrating strings of energy. These strings could exist in multiple dimensions beyond our observable three, implying that our universe is just a slice of a much broader, multidimensional reality. Loop quantum gravity, on the other hand, proposes that space and time are quantized, that they are made up of tiny, indivisible units, like pixels in a digital image. If this is true, then perhaps the singularity we associate with the Big Bang never existed at all. Instead, our universe could have bounced from a previously contracting universe into expansion, creating the illusion of a beginning where there was actually a transformation. This Big Bounce theory provides a compelling alternative to the traditional Big Bang model. It implies that universes undergo cycles of birth and rebirth through contraction and expansion, echoing the rhythm of existence across infinite time. These concepts, while deeply theoretical, point to one profound idea: the origin of our universe may not be the origin of everything. Rather, it might be a phase, a moment in a much larger, far more complex narrative that stretches beyond our comprehension. And yet, despite all these theories, models, and thought experiments, the truth of what came before remains elusive. We are like explorers on the shore of an endless ocean, glimpsing faint outlines of something vast beyond the horizon, guided by mathematics, physics, and imagination. What existed before the Big Bang? Was it a void filled with quantum potential? A collapsing cosmos giving birth to a new one? A timeless multiverse endlessly branching into realities? Or is the question itself a reflection of human limitation, our need to impose beginnings and ends on a reality that may have neither? As we continue to push the boundaries of science and thought, perhaps the greatest mystery of all is not just what lies before the Big Bang, but how the search transforms us. The deeper we look into the cosmos, the more we learn about our own place within it, not as separate observers, but as participants in a grand, unfolding story of existence. Reveal new understandings of the universe's earliest moments, these waves could serve as the echoes of the Big Bang. Should they be identified, they might provide proof of the universe's previous state. The possibility of discovering gravitational waves in their early stages is one of the most exciting prospects in cosmology today, because it might reveal more than just the truth regarding the Big Bang. It could also provide a glimpse of the cosmic state that existed before our universe was born. This theory offers an enticing prospect, locating gravitational waves that could act as fingerprints of a pre-Big Bang universe. As we continue to explore what could have existed before the Big Bang, we investigate ideas that push the limits of our comprehension, challenging even our most fundamental assumptions regarding space, time, and existence itself. One of the most mind-boggling ideas comes from the realm of quantum gravity, a field that seeks to merge quantum mechanics with general relativity. This merger could potentially reveal a unified theory of everything and might offer insight into what existed prior to the quantum Big Bang. According to quantum gravity, time and space are not smooth, continuous entities as we experience them, but instead are discrete, granular structures. This theory proposes that the space-time fabric itself could have been formed from a microscopic structure at the Planck scale, with tiny quantum fluctuations shaping the universe in ways we do not yet comprehend. From this perspective, what we perceive as a smooth space-time continuum may have emerged from fluctuating quantum fields. Thus, the before the Big Bang could be described by a completely different idea of reality, one where space and time themselves were not yet fully formed. Another possibility is that the universe is one of many in a vast cosmic landscape of possible universes, each with distinct physical characteristics, laws, and constants. This theory, known as string theory, is the source of the string landscape hypothesis, which suggests that all fundamental particles are actually tiny strings that vibrate within this framework. There are numerous configuration options for these strings, each corresponding to a distinct set of physical laws. The string landscape might suggest that our universe is just one of many, each emerging from its own distinct Big Bang-like event. The existence of such a landscape also introduces the idea that other universes might have different dimensions, different strengths of gravity, or even different types of matter. In this view, our universe might not be unique, but rather part of a collection of universes called the multiverse, each evolving independently. The multiverse theory provides a speculative yet fascinating answer to the question of the universe prior to the Big Bang. Another universe, arranged in a different way, could have led to endless cycles of development and devastation, without a definitive origin. In addition to these cosmological models, some theoretical physicists have also considered the role of black holes in determining the character of the universe. A hypothesis gaining traction suggests that our universe may be the result of a black hole formed in another universe. In this scenario, the singularity at the center of the black hole could serve as a gateway to another universe, with the Big Bang being the moment such a black hole gave birth to our cosmos. This hypothesis is supported by the fact that, according to general relativity, the singularity at a black hole's center is a point where space and time curve infinitely, creating a region where the known laws of physics may fail. The extreme conditions inside black holes may result in the development of new universes, which may suggest that what we consider the Big Bang was merely the birth of our universe from the singularity of an ancient black hole. Exploring these concepts necessitates a thorough investigation of the very nature of time itself. Some cosmologists speculate that time as we understand it may have had no meaning before the Big Bang. If time began with the Big Bang, then there may have been no before in any conventional sense. According to this view, time itself might have emerged from a fluctuation in the quantum world, or from a primordial state where the usual distinctions between past, present, and future did not apply. This could lead us to rethink the concept of causality, which relies on the assumption that events happen in a linear sequence. If time did not exist in the way we experience it, then the issue of what came before the Big Bang becomes nonsensical, as there would be no temporal framework to support it. Further theories of cyclic time, as mentioned previously, suggest that the universe undergoes endless cycles of birth, evolution, and eventual collapse. In this model, the Big Bang could represent just the most recent bounce in a series of universe cycles that last forever. These cycles might not be identical, but could change in various ways, each with unique physical properties. According to this theory, the cycle of the universe would be an ongoing procedure without a genuine beginning or conclusion, rendering the question of before the Big Bang meaningless in the conventional sense. The idea that time itself might be cyclical implies that each and every Big Bang could come after a contraction and another big crunch, with the universe relaunching itself in a never-ending loop. Another avenue of investigation into the potential of the cosmos is its nature as a primordial liquid of bits and fields that existed before the formation of stars and galaxies. This idea suggests that, prior to the universe's rapid expansion, it was filled with a dense and hot mixture of elementary particles, including quarks, leptons, and bosons, all in a state of extreme energy. These particles would have been interacting at extremely high densities and temperatures, laying the groundwork for the formation of matter and energy. Various versions of this theory propose that this primordial soup existed in a quantum foam, where particles constantly emerged and vanished due to the uncertainty principle of quantum mechanics. The properties of this soup could potentially offer insights into the earliest moments of the universe, and by extension, what preceded the Big Bang itself. Ultimately, what existed before the Big Bang remains one of the most profound scientific mysteries. As our understanding of quantum mechanics, cosmology, and fundamental physics expands, new hypotheses will continue to emerge, offering increasingly complex and occasionally paradoxical explanations for our universe's origins. Though we might never fully comprehend what came before the Big Bang, the pursuit of this knowledge will continue to push the boundaries of human curiosity, motivating us to investigate the unknown and explore the very edges of existence. As we delve deeper into these cosmological frontiers, new technologies and experiments are being developed to probe the earliest signals of the cosmos. Instruments like the James Webb Space Telescope, cosmic microwave background detectors, and gravitational wave observatories aim to collect data that could validate or challenge these theoretical frameworks. Every new observation has the potential to either reinforce our current understanding or force a complete re-evaluation of our place in the universe. Some scientists are even venturing into more speculative territories, suggesting that the universe could be a simulation or projection of information encoded on a distant boundary. This idea, known as the holographic principle, posits that all the information contained within our three-dimensional universe might actually be encoded on a two-dimensional surface. If this is true, then what we perceive as the Big Bang may have been the moment this projection began, a kind of informational event rather than a traditional explosion of matter and energy. In parallel, certain interpretations of quantum mechanics, such as the many-worlds interpretation, suggest that every quantum event creates a branching of realities. If applied on a cosmic scale, this could mean that countless universes emerge with every quantum fluctuation, each with its own unique timeline, laws, and possibly its own version of a Big Bang. The implications are staggering. Not only could other universes exist, but every possible universe might exist, somewhere in this vast quantum multiverse. And yet, for all our theories and observations, the nature of time, space, and origin remains elusive. It is a humbling reminder of how much remains unknown. The question "what came before the Big Bang?" may ultimately be less about finding a definitive answer and more about the human drive to seek meaning, to explore the unknown, and to understand the profound mystery of why anything exists at all. Our exploration does not merely satisfy curiosity, it challenges the limits of science, stretches the imagination, and invites us to rethink the very foundations upon which we build our reality. In this quest, we are not only searching for the origins of the universe, we are, in a deeper sense, searching for ourselves.